Yeah, no. I straight looked at it and I'm like, I give you credit for just finding the rule correct. I would agree with that. For the first ask your question.
All right. So, today we'll cover 2 sessions in the book, but probably, we'll see how we do with the time. There might be part of section 4.2 that we'll cover after the test if we are not, we are not doing too well. So today we'll see derivatives at work to understand the properties of the function that they describe. So we consider a certain function and we try to, understand. I mean, we write down a function. We try to understand its graph based on the knowledge of the derivative. So just to make a very simple example here, let us consider the function f of x equals to x squared plus 1, right? So this is a function that everybody should know how to sketch, right? This is a parabola with vertex at the point 0, 1, right? So, okay, look at me when I sketch the parabola. So if I start like from minus infinity, right? Then the values will decrease, right? And then we reach a plateau here, which will be at the vertex, right? So the function, the values of the function goes down, 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 down. And then they stabilize. And then the function keeps going up, right? So the point of components 0, 1, which is the vertex of the parabola, is a special point because it's where the function, quote unquote, stops being decreasing and becomes increasing. Or if, for the physicists among us, the point 1, 0, 0, 1 is a point of equilibrium, right? So if you think of the parabola as like a valley, right, or a cup, right, the bottom of the cup is a point of equilibrium, right? So if you put like a little ball here, for example, it will tend to go toward the bottom of the cup, right? So that is, if you study a little bit of physics, you know the formal definition of point of equilibrium. So anyways, that is how the graph of the parabola looks like, right? So what does it mean that is decreasing? So let me give you the formal definition. We say that a function, so let a function f from R into R. So we say that f is decreasing in an interval AB if for every x1 and x2 in AB, the function at so if x1 is less than x2 implies that f of x1 is less than f of x2. No, I'm sorry, I said decreasing. I should have said increasing for this definition. And we say that f is decreasing if x1 less than x2 implies that f of x1 goes exactly in the opposite direction, f of x2, right? So in fact, let's look at the graph of this function. So, I mean, increasing, roughly speaking, it means that this goes up, right? And let's test the x1 and x2 stuff here, right? So if I have x1 and x2 here, so the values of the function, so I have x1 less than x2, right? X2 is larger, and the values of the function at X2 is also larger, right? Hmm? Exactly, f of X2, right? So f of X1, the value of, at X1 is larger than the value at X2. Hmm? That means it's going up, right? That is exactly what I said here. Right? So here I use the X1 less than X2 and the f of X1, but this is the same. I mean, the same idea if I would consider the larger values instead, right? On the other side of the parabola, exactly the opposite happens. If I have two values, so that is X2, no, sorry, that is X1, which is the smallest, and that is X2, which is the largest. You can see that the opposite happens, right? So X1 is less than X2, right? But the values of the function, f of X1 here, is less than is greater than f of X2 there, right? So the opposite happens for the parabola on the other side. And in general, it happens to every function, to every decreasing function. So, for example, consider another function here, that again we are familiar with, f of x equal to sine of x, right? So we sketch the graph of the function, say, it's an infinite graph, right? But let's say that we start at 0, we finish at 2 pi. So now, can you tell me where the function is increasing and where the function is decreasing? Yeah.
From 0 to 1, it's increasing.
0 to 1.
Is 1, are we sure? What's the value?
Oh, that's pi over 2.
2, right? So with my color code, I should sketch this part of the graph in orange, right? Orange for increasing, right? Increasing here. And now, in which other interval is the function increasing?
3 pi over 2.
3 pi over 2.
All right, 3 pi over 2. 2 pi, right? The function is increasing. And in the rest of the domain, in this interval, from pi over 2 to 3 pi over 2, the function goes down, right? It's decreasing. All right, so let's see what going down means. Whether we can understand whether a function goes up or down, even if we don't have the graph in front of us, right? So let's go back to this parabola here. And so let me eliminate some of the, f of x1, etc., to make the graph clearer, right? So here we have a function that goes up when x is greater than 0, goes down when x is less than 0, right? So let's consider the tangent line at the points of the graph. So say, consider, for example, the point x2 here, right? So the function goes up, and in that, the behavior of the function is the same behavior of the tangent line, right? The tangent line goes up too, right? On the other hand, when we are on the other side, where the function is decreasing, the tangent line goes down, right?
Okay.
So the tangent line points down. Here instead, the tangent line points up. So a function is increasing. If a function is increasing, then its tangent line is increasing too. If a function is increasing, its tangent line is increasing. If it's decreasing, its tangent line is decreasing, right? Now, a line which is increasing, it has a slope in a certain way, right? So, for example, this line, what is the slope of this line? I'm not asking you a number, of course, because I'm not giving you a point, but is that positive or is that negative?
Positive slope.
It's positive because it's increasing, right? The function, you have done, that class called precalculus, or so I hope, lines of all kinds, right? So I'm sketching 4 lines here. So that is the line 1, that is the line 2, that is the line 3, and that is the line 4. Tell me which of the 4 lines have a positive slope?
1, 3, and 2.
3 and 2. Which line have negative slope?
4.
4, because it goes down,
Yeah.
right?
Mhm. Yes.
If you are not convinced, review your lines when you go home tonight, okay? Because, you know, that is very important. So now, the slope of a line, the slope of the tangent line, it is the derivative. That is why we are so interested in the derivative, not because it's pretty, which is not most of the times, but because it is related in a very strong way to the tangent line, to the curve. So the slope of the tangent line, so here we have a slope is greater than 0. That means that the derivative at x2 is greater than 0, right? And here we have the slope negative. That means that the derivative is negative, right? So, conclusion, the derivative is an indicator of the increasing or decreasing of the function, i.e., I just showed you that if a function is increasing, then its derivative must be positive. But the opposite also happens, because you know the function and the derivative are very tied together, you know, in a little neighborhood of the point. So what I can state for you is the following, you know, theorem, right? I'll write that down here. So theorem: a function f is increasing in an interval AB if the derivative of the function, it is positive in AB. It is decreasing if the derivative of the function is negative in AB, right? So the function, the derivative, the sign of the derivative tells you a lot of information about the function, but we are not done yet, right? So remember the point where the function stops being increasing and decreasing and becomes increasing and vice versa, right? Which is the vertex of the parabola. What is the tangent line at that point? The tangent line is flat, right? It will have slope 0. So at the points where the slope is 0 are very important because we are kind of the turning point of the function, right? The function is like where the function changes from being increasing to be decreasing and vice versa. So let me give you a definition of critical points, and then how to understand which critical points do, you know, are like the parabola, or maybe they are in a different way. So definition: a critical point of the function of f of x is a point where, x0 same, where the derivative of x0 is equal to 0, or f0 prime does not exist. So you want points where either the derivative is 0 or it doesn't exist. And these points are interesting for us and will need to be studied carefully. So before I give you more definition, let's consider a test. The parabola we've done, right? The parabola is very clear. So let's take another parabola and let's see what the derivative tells us, right? The derivative in particular will tell us where the vertex of the parabola is. So let's consider the following parabola. f of x equals to x minus x squared plus 3. Everybody agrees that this guy is a parabola, right?
But it's
Yes. Yes.
Why it's a parabola?
um,
Because the highest power is x squared, right? And then there is no, for example, if it was x squared, square root of x minus x squared plus 3, it would not be a parabola, right? You want a polynomial, you don't want some strange thing. All right, so now this is, so we expect some parabola. And how do you expect the parabola to be? You expect the parabola to face up or to face down? To face down, and why that? Why is that?
Negative.
Because of the negative. All right, let's see whether we are right or not. So we do the derivative of the parabola, and the derivative of the parabola is 1 minus 2x, right? So now 1 minus 2x, that will give us the slope at every point of the graph. So we want the parabola to be, we want the slope to be greater to 0, right? To see whether it's increasing. Or maybe we'll do that. Maybe we'll do directly the critical point here, right? We set that equal to 0, and that will give us the point where the tangent line is horizontal, or the critical point, right? So we solve for x, and that will give us x equal to 1/2, right? So now x equals to 1/2 is the critical point, right? And that will, at this point, the derivative will be 0, and that will be the vertex of the parabola, because we know already what to expect, right? So now let's see whether you are right and whether the parabola looks like this or whether it looks like that. So let's see whether the derivative is positive or negative. So if you want to study the derivative, the sign of the derivative, we can see, for example, where it's positive. And again, we solve the inequality for x, right? So there would be 2x, so 1 greater than 2x. I'm bringing 2x on the other side. And so that will give us, we divide by 2, so that will give us x less than 1/2, right? So that tells us that the derivative is positive if x is less than 1/2. That's a bad inequality. There will be many pretty inequality to come. So when x is less than 1/2, the derivative is positive, right? So that's a plus. But again, if you are not sure of your inequalities, and knowing the history of algebra of this class, probably you will not be sure of this inequality, like solving an inequality. I want you to do a test to test some point, right? So, for example, you can see like the point 0, right? And plug 0 into the derivative. So at 0, the derivative is 1, right? So f prime of 0 equals to 1 greater than 0. So, okay, the derivative is positive at 0. We are doing right. And on the other half line, the derivative is negative, right? So, okay, so, and now what? What do we do with this information? So we have 1/2 here, right? The derivative positive means that the function is increasing, right? It goes up. So the function goes up, right? For x less than 1/2. Then here is our vertex. Oh, thank you. And then it's going down. All right, thanks. And so, see, the function looks like this, right? It looks like a little mountain now. Okay. All right. So, if I want to sketch this function, how do I sketch it? Well, when x is equal to 1/2, that's going to be our vertex. And if I plug 1/2 in here, I have what? I have, f of 1/2 equals to 1/2 minus a quarter plus 3. So would be 2 minus 1 plus 12, so would be 13 quarters, right? So that's somehow here, 13 quarters. And that's my vertex, and then the function will go down, right? Will be like this. So it's increasing here, right? Increasing and decreasing there, right? That's the parabola we are expecting. All right. So once again, what I did is I mean, more or less we knew what to expect, right? Because that's a parabola that you have seen already a million times. But the derivatives, right? It tells us whether the function is increasing or decreasing, and so we find the critical points. That is the zeros of the derivative. We see whether the derivative is positive, and then the derivative is negative, and then we sketch the function accordingly, right? So now we'll do a million more of these examples, this is 4.1. Actually, I'm doing like 4.1 and 4.2 together, because in 4.1 it's about increasing or decreasing and concavity and convexity. Instead of 4.2 is about the relative maximum, relative minimum, right? Yes.
I understand when you get x is less than a half, and then from there, I don't see the connection.
So x is less. So I studied the inequality. So my question is, for which values of x is the derivative positive? So question mark, right? So that's, I want to see for which values of x this expression is positive. I solve for x, I solve the inequality for x, and I get x less than a half, right? So what does it tell me? It tells me that the answer to my question is, for x less than a half, my derivative is positive. So derivative positive means going up. Slope positive, it means going up. So for all the values of x for which the derivative is positive, the function is going up.
Okay.
For all the values, if the function is not positive, then it's going to be either 0 or negative, right? So for all the values of x which are greater than a half, the function is going to be negative. The derivative is going to be negative, and so it's going down, right? So let's see another example that will have a little bit more interest. So blah 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 blah. My list of example. Okay, let's do that. For x to the third minus 12x squared plus 2, right? So that's a polynomial of degree 3, so it's not a parabola anymore, right? It's going to have more twists or turns. So let's see exactly how the polynomial behaves here, right? So we do the derivative of this polynomial, and we get what? What's the derivative of this guy?
X squared minus 24x.
Minus 24x. The derivative of 2 is 0. All right, so we set this derivative equal to 0. We can factorize 2mx, x minus 2 here, right? And set that equal to 0. So of course 12, it doesn't matter, right? Okay, I want you guys to get used to eliminate the things that don't matter. For example, 12, it doesn't matter in this conversation, right?
You divide 12 on both sides.
Exactly, because 12 is never 0, it's a number, right? So we can divide by 12 and dispose of it. But x does matter, right? Because x is equal to 0 at 0, right? So the solutions are 2, x equal to 0 and x equals to 2. So now you should remember from precalculus how to solve the inequality. X times x minus 2 greater than 0. But I don't want to go into it because it would be really too tedious. I'm sure half of the class has forgotten. So I want to teach you the test point method, right? If you know how to solve this inequality as seen in precalculus, then do the way you're used to. But I'm going to teach you, in class, I'm going to do examples using the test point because I think the other method is, too long, maybe, take too long and be confusing for a good part of you.
Okay.
So now we want to see whether, again, the derivative x minus 2 is greater than 0, right? So now what's the situation that we have? The situation is that, we have a line, we don't know what the derivative does at the single, individual points of the line, except that, at 0 and at 2 we know, right? We know that the derivative is equal to 0, so the tangent line will be horizontal. Now, let's pick up a point 1, say between 0 and 2, right? And let's ask the following question. F prime of 1, is that greater than 0? And how would you answer to this question? You just plug 1 into the derivative and tell me what it is, right? And it's negative, right? Because f prime of 1 is 1 times minus 1.
It's minus 1.
It is certainly negative, right? And so the answer to this question is no, it is negative, right? So now I claim that between 0 and 2, there can't be any point where the derivative is positive. I.e., I claim that in the whole interval between the zeros, right, between 0 and 2, right, all the points of the derivatives are positive, right?
Okay. Yeah.
So why am I claiming that? So let me tell you what I claim. So I claim that f prime of x is going to be negative for x between 2 and 0. And why I'm making this claim?
You want? You could say that just because you already figured out the critical points. If you figure out the critical points, there would have to be another critical point in between in order for it to switch.
Very good. So suppose that here is 0 and here is 2, right? So here at the point 1, I already figured out that my derivative is negative, right? Minus 1, sorry. So, like, if there is a point by any chance where the derivative is positive, right? Say if there is a point where my derivative takes the value 3, for example, right? Then, by the intermediate value theorem that I know that Roberto has mentioned in class because I've seen the theorem improperly cited in the test 1, right now is the time to cite it instead, right? So if the function takes the value minus 1 and it takes the value 3, for example, it has to take all the values between 1 and 3, right? In other words, I have to go from here to here without interruption. And so there has to be another point where the function is 0, right? Or if you prefer to think this way, well, I know that my function is negative at 1. It's going to be, say, if it was positive at some other point, then in order to go from negative to positive, I'll have to cross the x-axis. So there will have to be another critical point.
Okay.
That's not possible. So if I test the 1 point, right, then that 1 point determines the color, quote unquote, of the whole segment between the critical point.
Okay.
So here the function is negative. So it means that my function, I mean, the derivative is negative. It means that my function is going to be decreasing. Now, let's see what's happened at point -1, for example. I'm taking another point outside, of the interval here. So, and my question is whether f of -1 is greater than 0. And the question is now yes, right? Because I have -1, -3, and that's positive, right? Product of negatives. And now another point over here. So it means all this, the half line is going to be colored in blue, right?
Okay.
And now here is 3. Let's pick up a point 3, for example. So I have f of 3 now, I mean f prime of 3. And again, greater than 0, question mark. And now the answer is yes. Because if I plug in 3, I get 3 times 3 minus 2 greater than 0, right? So now what's happened then? It happens that the function is increasing here.
Okay.
Right?
And decrease.
Increasing means the function is going up. It's decreasing
Decreasing
there. And it's
increasing.
increasing here. So, all right, look at how we sketch the graph of this function. So we always start from the critical points, right? We always start from the critical points, and we work from there, right? So now the critical points are at 0, right? Now I'm doing the graph, so now I'm not talking about the derivative anymore, okay? So at 0, I want to, and remember my function is for x cubed,
-12x.
minus 12x squared plus 2, right? So f of 0, so the value of the function at 0 is equal to 2. The value of my function at 2 is equal to what? 4 by 8, 32, minus 12 by 4, 48, plus 2. So that's going to be minus 14, right? Minus 14, so that is 2. At the point 2 here I have minus 14 all the way down. Right, and now let's we need the graph of the derivative to go from critical point to critical point, right? So the function is increasing, right? So that's the graph of the derivative over there, right? So the function must go up to here, right? So increasing. Then it must go down to this point, right? Up, down, and then up again, right? And here is your graph. Again, you get the critical points, you start from the critical point, right? You have to use the sketch of the derivative to figure out the rest of the graph, right? All right. Yes.
So then to be able to establish, so then you get the derivative, you find the zeros, the graph, the derivative is 0, and then from there you plug in those points, 0 and 2, into the original function to be able to sketch the graph. Okay.
That's right. And then you study the derivative by picking up, for example, test points and decide whether the derivative is positive or negative, etc. And that will tell us whether the function is increasing or decreasing, etc. Right? So, okay, but okay, now I want to plant the seed of the doubt here, right? Are we sure the graph is correct? Who told us that I can start from minus infinity, for example?
Okay.
Maybe what if the function instead goes, if it goes to an asymptote or something?
Yeah, true. Yeah, prefer
Not
to
really.
see-
What if I sketch the graph of the function like this? There is no critical point, right? It goes to an asymptote, it still goes up. So in order to contradict me, you have to tell me what's happened at infinity. So if I do the limit of this polynomial as x goes to plus infinity, I get what? Plus, if I do the limit at minus infinity, I get what? Minus infinity, right? So at minus infinity, when x goes to minus infinity, I expect the function to be negative all the way down to here, right? So I start from minus infinity, go all the way up, blah, 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 goes down, go up, and I don't do this because if I would do, if my graph will go toward an asymptote, that will be the limit of the function at infinity, right? I go, instead of, doing this, I do exactly what I did before, so I go to plus infinity, right?
Okay.
All right, we'll do many other examples here, but okay, before we do this, I need to give you a couple of more definitions. All right, so definition. A point, a critical point x0 is a relative maximum for a function f of x if the function f of x, it is less than or equal to f of x0 for x near x0. A relative minimum, so it is a relative minimum if f of x is greater or equal to f of x0 for x near x0. It is an inflection point. So, okay, I want to keep this definition on the board, the definition of critical point, because it's important that you, realize that it's, so x0 is an inflection point. If f prime of x0 is equal to 0, but x0 is not a maximum nor a minimum, not a relative maximum, nor a relative minimum. So, what are we saying here? A critical point is a relative maximum for f of x if it's like the peak, if the top of a little hill, right? So that's the point here is certainly a relative max, right?
Maximum.
Do you see a relative minimum in this picture?
Yes.
At negative 14. No, a little bit past negative 14.
That's the relative
About 2
minimum, right? That will be the bottom of a cup. You know, the relative minimum is the lowest point in a portion of the graph. Of course, the graph has no absolute minimum, right? Because the graph goes all the way down to minus infinity. But if you restrict your attention near the critical point, then the function looks like a cup, right? It looks like a, you know, in this area here, no? And the bottom of the cup is your relative minimum, right? So that's a relative minimum. Do you see any inflection points? Again, the derivative is 0, but the point is not a maximum nor a minimum. We have only 2 points where the derivative is 0, right? And these 2 points are accounted for. So for now, then we give you a more definition, general definition of inflection point, but for now. So, okay, how to see whether a point is a relative max or a relative minimum? Well, you can also go straight to the graph of the derivative, right? Because if I go up and then I go down, the peak here, you know, the point here will be a relative max, right? The point there will be a relative minimum. So, and how the graph of the derivative will be if we have an inflection point? And now I'm going to show you, right? So that will be a relative maximum, and that will be relative minimum. So, and how is the graph of a function with an inflection point gonna be? It will be like that. Okay, so we have f of x equals to 4 x to the third minus 4. For example, so now we do the derivative.
12 is x squared.
And what is the derivative?
12 squared.
It's 12x squared, right? So the derivative is 0. When is the derivative 0?
Absolute value of x.
At absolute value of x equal to. Sometimes when problems are too easy, you think that there is a trick, right? Yes, there is no trick. It's the derivative is just 0, right?
Okay.
At 0, so that's the only point. So x is equal to 0, right? So now the derivative is 0 at the origin. But then, you know, it's 12x squared, right? Away from the origin, it's always positive because it's a square of something, right? So it means that the derivative is all positive. The function is always increasing, right? Derivative positive means increasing function, right? So it looks like this, right? So f is increasing, right? So plus plus. And the f is increasing. So f is always increasing, right? So 0, which is our critical point, it is not a relative maximum because otherwise the function will look like this, right? Up, down. It's not a relative minimum because the function will be down, up, decreasing and then increasing. So this point here, it will have to be an inflection point. That's the third point that doesn't fit into the 2 categories. And the function here to this point looks like this. So, okay, again, we always start from the critical point. So what is the value of the function at the critical point? The critical point is 0, right? X equals 0. So here is negative 4. So the function is always increasing, right? Goes up, 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 up. So we start from negative infinity, right? And negative infinity, so will be like this. When we get to 4, to the point of coordinates 0, negative 4, the function is, you know, the tangent line is 0, right? It has log 0, so the function has to kind of become horizontal or almost, right? And then it will go up, 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 up. And here, the function, the tangent line will be kind of horizontal, right? So here is the graph of the function, a function with an inflection point. So 0, again, that's an inflection point. All right, so now we are ready to do a number of happy problems with, polynomials are easy, right? So but I'll give you another polynomial so that you will, see an easy problem before we upgrade to problems which are slightly more complicated. And these problems will make you realize that, when I say you simplify the derivative, it's for good reasons, right? So, but let's start with a simple problem here. So suppose that we take f of x equals to 3x to the fourth, x to the fourth, plus 4x to the third, minus 12x plus 2. So this problem is meant to have you simplify all the numbers, but don't get used to the good life, guys, because numbers sometimes won't simplify as nicely. Okay? So let's calculate the derivative here.
12x squared.
So who wants to give me this derivative?
12x squared.
Plus 12x squared minus 4.
12x squared. Minus
12, I'm sorry, there was a square here, 12x.
So, okay,
No, so there would be 24x, right?
24x.
24x. Okay. Now, what do? We have to solve set that equal to 0 because we want to find the critical points, right? So what do?
Factor out 12x.
And we obtain x squared plus x minus 2, right? Equals 0. So we can dispose of 12. In fact, I would want you to, dispose of the terms that we don't need to avoid confusion. We definitely don't need to have, yes.
If you have a term with an x that comes out, doesn't that mean that x equals 0 is a point?
Absolutely. X equals 0 is a point. You cannot dispose of x, right? Because x not only can be 0, but can be positive or negative. So x equal to 0 is definitely a critical point. But then we have to solve the equation x squared plus x minus 2 equals 0, right? And many of you, that should be easily to factorize. The problems in the book tend to be really easy in terms of numbers, but let's apply the quadratic formula to solve it, right? If we apply the quadratic formula to solve it, then what do we get?
1 and negative 2.
Don't want the solutions, I want the quadratic formula.
Negative 1 plus or minus square root of 1 squared minus 4 times negative 2. Yeah.
Minus 4 times 1 times negative 2, right? All over 2. Right? So we get what? The first solution is with the plus, it's minus 1, and then inside the square root we have, we don't have a negative number, right?
9.
We have
an imaginary.
minus 4 times minus 2 is plus 8, plus 1 is 9, right? Minus 1 plus 3 over 2.
Okay.
And minus 1 minus 3 over 2. So we get here 1 and there minus 2, right? As advertised, yes. I could have factored, but hey, the quadratic formula is good for your health, for the class health in general, because life will not always be as good as to have things that factorize easily, right? So we want to, make sure that the quadratic formula is not forgotten. All right, so we have also x equals 0. So we have three roots, right? Three critical points now. We have 0, we have 1, and we have 2, right? So 0, 1, and actually -2, right? So these are the critical points, and now we have to see what's happening between these critical points. And you know, you want to plug values, right, which are between these 3 points. So one thing I recommend you to do, you know, so this is your derivative, right? If you have the solutions, you know, the critical points, you want to factorize the derivative so that it will make easier for you, considering you won't have a calculator in the test, right? It will make easier for you to do the testing if you factorize the derivative, right? So the factorization here is, you know, x times x minus 1 times x plus 2 equals 0, right? So again, you know, precalculus in action, you factorize a polynomial once you know its roots. So now, look at how we can use the factorization efficiently. Let's pick, you know, how many test points do we need, guys? 2. 2? No. We need 4 because we need 1 here, we need 1 here, we need 1 here, and 1 here, right? So, for example, we can pick 2 here, we can pick, I don't know, 0.5 there. We can pick -1. You want -1?
Yes.
All right, -1. And what, -3 over here, -4, -3, -3. All right, -3 in here. All right. So now, let's see what's happened when we compute f of 2. F of 2 is, look, if you use the factorization, we have 2 times 2 minus 1, which is 1, times 4. You don't even need to calculate that. Just tell me whether it's positive or negative, okay? And it's positive. So now, f of -3 is equal to what? Is equal to x, right? So -3, -4, -3 plus 2, -1, right? -3 minus s, right? Now, f of, what else? What did we say? Oh, f of -1 here will be what? -1, -2,
Then 1.
and then 1.
That's great.
Greater than 0, right? F of 0.5.
Is it f prime 0.5 or just?
Oh, yeah, I'm sorry, it's F prime. Yeah, F prime. That is the derivative. I'm not plugging that into the original function, into the derivative. All right, F prime of 0.5 is equal to what? 0.5
Times -0.5.
-0.5 2.5, right? All right. So it is negative, right? But suppose no, let's do first as it should be, right? So that is negative, and then I'll show you what's happening if I make a mistake. Okay. So now, well, actually, I should have done that for last rather, because I want to start from you know, from -3 and then move onward, right? So now, -3, f prime of -3 is negative.
Yeah, it's slope is negative.
So the slope is negative. Okay. Right. So your hand starts from the desk and doesn't go up, right? It rather goes toward the floor. So down, yeah, because your hand was telling me a different story. So, okay, -3, the function goes down, right? Now, at -1, the function goes up. Okay? At, I mean, in here, the function goes down. and then it goes up again, right? So, okay, you want to sketch the picture like this. All right, if you do the graph correctly, you can answer all the questions in the quiz, in the test, in the homework, right? This graph is crucial for answering all the questions. So, if I ask you, for example, which points are relative maximum,
Zero.
Zero,
Just zero.
0 and 2.
0 is a relative max, right?
But 0, 2,
Yeah, exactly. The point, well, the definition is just for the x coordinate. A point x is a point of relative maximum is such and such happen. Then eventually the point in the graph will be the point of components 0, 2. Yes, that's right. So this is a relative max, right?
What is the relative minimum?
Now,
No, negative
the point, so which points are relative minimum? Negative 2 and 1, right? Is there an inflection point that you see?
No.
No, right? No, we don't see any inflection points here. So 0 is relative max, and minus 1, so minus 2 and 1 is a relative minimum, right? So, all right, so now we can sketch the graph of this thing. Yes.
Is negative 2 relative or absolute?
We don't know. It's not clear, right? Unless until we find the value of the function at this point, we don't know whether it's relative or absolute. Right? But that's a very good question. In fact, we'll verify that, right? So, okay, but before we move forward, let's make sure we are doing right. So the graph seems to indicate that the function comes from over here, right? The plus infinity. And then it goes down, and then it goes to plus infinity again, right? Is that correct? What is the limit of the function as x goes to plus infinity?
Infinity.
but we don't know because you're subtracting infinity.
All right,
Right.
exactly. We are subtracting the infinities, but we have learned also about the garbage rule, right? When we have a bunch of infinities, only the leading one counts because the others will have much less importance. Or if you prefer, you can factorize x to the 4th, and you will have 3 times a bunch of stuff that goes to 0, right? So this thing is like garbage, 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 garbage. So the result is infinity, right? Plus infinity. And if I do the limit as x goes to minus infinity, what's the limit now? When x goes to minus infinity, what do I see here?
It's going to be positive.
It's still positive, right? Because x to the 4th is always positive. So that is in agreement with this graph, right? That is in agreement with this graph, right? So it starts from positive infinity, right? So everything, this graph, it has to be done well. And if you do it well, then it tells you everything you need to know about your function, right? It has to be coherent with everything else you know about the function. So let's answer the question of your classmate, whether the point minus 2 is an absolute minimum or not. So again, when we sketch the function, we have to start from the critical point. So we want now to evaluate the value of the function. Okay, so now we don't need the derivative anymore. We want to evaluate the value of the function where? At 0, at negative 2, and at 1, right? So f of 0 is 2, right? We saw that already. At minus 2, it is what? 3 times 2 to the 4th is 16, right? So 3 by 16, 48. Oh, yeah, sorry, to say something else. Yeah, 3 by 16 is 48. Plus, so 4 by 8, so 32. Minus 48, so 48 goes plus 2, right? So
The positive 32, the 32, wouldn't that be negative?
oh, I'm sorry. Yeah, that's I'm sorry. That is negative 2, negative 2, negative 2. In fact, all right. That's actually a very educational moment here. I made a mistake. I didn't realize it was negative. I mean, I didn't think it was negative, and I said that that is positive here, right? So, okay, at this point in time, I would say, wait a moment. I have f of 0 equals to 2. F of 0 is here, right? And f of minus 2, it's going to be like 34. I don't think so, right? So I would know that there is a mistake.
Right.
I know that there is a mistake, right? So this is not a plus, but rather a minus, right?
Okay.
And in fact, it gives me minus 30, right? And that is coherent with my graph over here. F1 is 3 plus 4 is 7, minus 12 plus 2, right? 7 and 9 is minus 3. Right? So minus 30 is the absolute minimum, is the lowest point of the function. Yes, that's correct. So how do we sketch the graph of the function, right? So we start, that is minus 2, right? Minus 2. That is, somehow off scale, but it doesn't matter. You can be, also in your graph, I mean, in your test. I don't care for the accurate scale as long as your graph contains all the elements that it has to contain, right? So that is that point. At 0, the function is equal to 2, and then it has to be a maximum, right? And at 1, the function is minus 1, right? Right? So
Minus 3.
Oh, minus 3. Anyway, so now you look at the graph of the derivative, and I sketch the function by joining the critical points in a proper way, right? So I start from plus infinity. I get the first critical point. I go up, right? And I get to the second critical point. I go down, and then go up again. Beautiful. And this is not only a relative minimum, but it is the lowest point of the function, and so it's an absolute minimum. Okay? Okay, so let's see what time is it, because now I want to do a million of other examples. For 10. All right, so in the test, for 10, no, for 10, 545. No, so I can do the convexity also. Convexity and concavity. Yeah, no, I want to close section 1 with everything is in there. Otherwise, you will say, oh, well, so can I do this? Can I do that? It will be confusing for the homework. So, I mean, I will do all the section 1, but then there will be something in section 2 that I won't do, i.e. the second derivative test for the relative maximum or the relative minimum. So let me talk about concavity and convexity. So the concavity we consider the function f of x equals to x squared, right? And we consider the function minus x squared. So one function is a parabola that goes up. The other function is a parabola that goes down, right? And these two functions, so many other functions have the same behavior, right? For example, if you look at this graph, you can see that for part of the graph, the function looks like a parabola that goes up, and then it looks like a parabola that goes down, and then it looks like a parabola that goes up again, right? So the behavior of being rounded up in a nice way, it is called convexity or concavity. Well, the book actually uses the word concave up or concave down. So the definition is, so the book uses a slightly different definition. It says that first derivative is increasing, but I want to use go straight to the definition that you can use. So we say that f of x is concave up in the interval AB if the second derivative of f it is positive in AB. So I'm doing the U very big, so to indicate that the function looks like a parabola that goes up, right? So f is concave down with a big N, so to indicate, what the function should do, if the second derivative of f is negative. So here, this is, the parabola is the prototypical concave up function, and that is the prototypical concave down function, right? Why? Because, if you consider the first derivative here, that is equal to 2x, the second derivative here is just 2, and that is greater than 0, right? So the second derivative is positive everywhere, function is concave up, right? And here, the first derivative is minus 2x, the second derivative is minus 2, negative, right? And so that's again concave down. So sometimes it's easy to study the second derivative and see, the second derivative serves to make a prettier graph, like the graph, for example, here it's, I didn't make it too accurate, right? The transition point is not clear where it is. But it also has other purposes that we will see after the test. The second derivative is actually very important in understanding how a graph looks like. So one more definition. So an inflection point so that is the second definition that I gave you about inflection point, but now we are talking about the second derivative, so this definition is actually more general. An inflection point for f of x is a point where the second derivative of f is equal to 0. So in particular, the definition I gave you earlier, where the derivative is equal to 0, but the point is not a maximum or a minimum, it will be a point where the second derivative has to be 0. So, but let's we play with this definition for our next example. I just, probably you deserve a little break now. So I just wanted to give you a lot of definitions. So we'll spend the rest of the time doing problems here, and maybe doing also problems on implicit differentiation, okay? Insurance companies So 2.4 were in the test. 2.5. Yeah, 2.5 was in the test. That's right. Yeah, that's actually the idea. So 2.6, it's going to be 2.6, yeah, 3.1, 3.2, 3.3, and 3.6, yeah, that's right. And then part of 4.2.
See what? Okay. Kick my ankle this one.
Oh.
Sure.
No, it's to the right. Put it to the right. I thought you did.
No, actually, because there is a link and a lead.
Oh.
And so, Annalene, you were.
If you think about it, yeah.
Because I remember you missed, you missed the quiz.
Oh, yeah.
No, it says she just came straight to class. She didn't show up to your office for it. She took it in here.
I didn't make that because I teach her. Like, you need to worry about
I see. And so it should be with the
Yeah.
other bits.
I'm gonna get home and like,
Oh,
figure
yeah,
out what this problem is. Yeah, I think so.
Yes, I
And
think
tomorrow,
it's gonna
what's
say
the
because
problem?
it was
And
called,
the day after that,
yeah.
what's the problem?
Yeah, okay, very good.
But that's what I did for zero. I literally like, I make I literally did all of the problems that I did, and I got what you don't have. I didn't do that for the second and for test one. I didn't do that.
I don't know. I don't know why nobody does that.
I guess I just wasn't sure what to expect.
Typers. Okay, that's what you
What flavors do you like? Cherry?
Usually red first.
So it's like, I always eat my food before I don't know, I don't have it. Yeah, like 2 sandwiches in like 4 hours. I'm so hungry. Just like. Well, I've been out and about, but I've been here like since 12. Yeah, I don't know. Well, like halfway through, I like, oh, Professor, you know what I noticed? For the quiz, I kind of screwed it up. Because when you had put on the board, I had positive, and I thought we were supposed to put negative. But then I figured, then I realized not everyone had the same thing.
Yeah.
So I thought it was the other way around. Like I was supposed to put a negative instead of a positive.
No,
if I had
said the positive instead of the negative.
Yeah, I don't. Yeah, it screwed me up. So I changed it in my test.
And how did you
I have-
calculate the
I have
logarithm
no
of a
clue.
negative number?
That's what I was freaking out about. I was like, how? That, and then I got stuck on that.
You know, when in that task.
I know. I just. It was like, because I was beating around it because I did it, and I was like, okay, that seems simple
Yeah,
with the positive one.
of course.
But
and
that's-
why did you change it? Who told you to change it?
Because I don't know. I like didn't read it proper. I don't know. But anyways, yeah.
Anyway,
So you'll see what I did in the quiz. It's not that I didn't.
Hopefully it's not terribly important.
I got so confused.
Limits.
Yeah, I know. It was just I got like really stuck on that. I don't know. I guess I didn't time manage. But yeah, I think for next time if I get stuck, I'll just skip it.
Just ask or ask.
Or ask, yeah.
Yes, exactly.